All right, kiddos, here's the graphic that we didn't have a chance to adequately address in class. This graphic is in section 4.5 in the Oxford textbook, and it's going to be really important that you can look at these waves, describe what's going on, and identify which harmonic is present at each of these. Okay. So what you're seeing here is a tube, right? A pipe. That's the black outline here. So on the left, you've got a pipe, kind of just like, I don't know if I've got one here easily available. Okay. Just kind of like a PVC pipe you can think about, like from our twirling stopper lab, except it's closed on one end. There's a cap. Okay, and what's going on is you're sending a sound wave into the pipe. What does that look like? You could yell into the pipe, you could blow, you could use a tuning fork, or you could even like make a sound. There are tone generators on your phone that you could send into the pipe. Right? Each of those sounds has a specific frequency. Now, each pipe of each length has natural frequencies at which it will produce the loudest volume. Okay, that's called resonance, right? Every object, whether it's my coffee cup, right, my calculator, any object has a frequency at which it naturally oscillates, and that's called resonance, right? And at the frequency at which a object naturally oscillates, it produces a higher volume of sound. Okay, so here on the left, if we've got a closed end pipe, if we send a sound wave into the end, you will naturally get the maximum volume for frequencies of sound associated with 1/4 of a wavelength, 3/4 of a wavelength, 5/4, 7/4, and 9/4 of a wavelength. If those will fit exactly inside the pipe. Right? What they've got here is a visualization of a transverse wave that is representing a longitudinal wave. Okay, so let's look at this 3/4 wave. This is telling us that 3/4 of a wavelength is fitting inside of this pipe, right? Outside of the pipe, a full wavelength would look like that. Right, so 3/4 of it is fitting inside the pipe. Now, what is going on is we've got an incident sound wave, which is this solid one. The incident sound wave is going into the pipe. That's whatever sound wave you're sending in. Okay, that incident sound wave is going in. When you've got a closed end of your tube, that acts like a fixed boundary. If you remember our PhET simulation, the closed end of the pipe goes into the tube, or the sound wave goes into the tube, the sound wave hits the closed end of the pipe, and that acts like a fixed boundary. Waves that are reflected off of a fixed boundary are reflected and inverted. Reflected and inverted. And so that means if the incident wave is coming in and it's reflected and inverted, it's always going to experience destructive interference right at that closed end. So we get a node. Okay. And we'll end up with a high pressure region, right? High pressure, high amplitude, a lot of air particles moving around. Here's another node, which is low pressure. And then if there's 3/4 of a wavelength within this pipe, you'll end up with a high pressure region right at the mouth of the pipe. And it's those high pressure regions that produce the high volume of sound. And so you really want those antinodes to be at the opening of the pipe to produce high volume and get that resonance effect. Okay, so for pipes that have one open end, there will always be a node at the end of the pipe, and the sound wave is reflected and inverted, producing a standing wave inside the pipe, and you'll get maximum volume when there is a high pressure region, right, an antinode of the sound wave at the opening. So you'll see the first possible time an antinode could be at the opening is if 1/4 of a wave is inside. 1/4 of a wave because you're just going up to a maximum, down, right? That would be the full wave. Here we've got 1/4 of a wave. And we could say, for this, we could say the length of the pipe is equal to 1/4 of a wavelength. And so if we knew the length of the pipe, we could find the value of the wavelength. Okay, here, the length of the pipe equals 3/4 of a wavelength, and so on and so forth. All right, so for one open end, these harmonics aren't as simple as first, second, third, fourth. We call these harmonics for one open end. We actually call them the first harmonic, the third harmonic, fifth, and seventh. Okay, so there's no 1, 2, 3, 4, 5. The pipes with one open end resonate only in odd harmonics. Okay, so that's something that you're going to have to memorize. There will be problems. The IBO does this where they say, okay, so you've got a pipe with one open end. Find the wavelength. It'll give you this diagram. It'll tell you the length of the pipe. And they'll say, find the wavelength of the wave when it's at its third harmonic. And you'll have to know that it is the second time that that pipe could experience resonance, right? The first harmonic, the first time the pipe could experience resonance is when there's an antinode, right, at the opening, and there's 1/4 of a wavelength inside. The second time it could experience resonance, the second time it could possibly have an antinode at the opening is if 3/4 of a wavelength is inside. Even though that's the second time that pipe could experience resonance and an antinode at the opening, it's called the third harmonic. A way to remember that is that for the one open end pipes, the wavelengths always fit a certain number of quarters of waves. And I like to remember for one open end, how many quarters of a wavelength fit inside the pipe is the number of harmonics. Okay, doesn't make sense. It's just how I remember it. Okay, now with two open ends, what you get is there's no fixed boundary. Okay. There's no fixed boundary. The pipe is open at two ends. So for it to resonate and produce the highest volume, you'd have to have an antinode at both ends. Okay, so here we can see antinodes at both ends. Okay, this is half of a wavelength, kind of cutting the ends of that wavelength off. Do you see that? So half of a wavelength, the length of the pipe encompasses half of a wavelength. Here, the length of the pipe encompasses one wavelength. And that looks weird because there's like half of a wavelength here and then 2/4, and you add them together and you get a whole wavelength. Right? The next time that the pipe could experience resonance and have 2 antinodes at the opening is if you've got a full wavelength plus another 2/4 added together makes a half. So 1.5 wavelengths. Okay. For a pipe with 2 open ends, the harmonics just go up sequentially. So it's first, second, third, fourth, fifth. Okay. And so the type of problem that they would give you with this is they would say, all right, the length of, let's say we've got 2 open ends, and the length of the pipe equals 50 centimeters or 0.5 meters. And it's oscillating at its third harmonic. Okay, so that the length of the pipe is equal to the third harmonic, 3/2 of a wavelength. And so that means that the wavelength is 0.5 times 3/2, or 0.75 meters, right? That you can find the wavelength from that. If this is happening in air, then the speed of sound in air is 334 meters per second. Remembering off the top of my head, like 330 or something like that. The speed of sound in air is 334 meters per second. What's the frequency? And you can just use the equation speed equals wavelength times frequency to find the value of the frequency of that particular sound that is resonating in a pipe at its third harmonic, and that pipe is 0.5 meter long. All right, so that's the type of problem that we're looking at here. All right, please make sure that you've got detailed notes of this diagram and some way in your mind to remember the names of the harmonics and what that looks like for a 1 open-end pipe and a 2 open-end pipe. Please let me know if you have any questions. All right, kiddos. See you soon.